All right, this is day 2 of the OSG Virtual School 2021, and I'll start with a presentation on today's topic. There will be a demo toward the end, but I will also pause several times for verbal questions and to cover any questions that have come up in the chat. The other instructors will be able to handle some of those while I'm talking. But today's topic is the execution of high throughput computing work via the HTCondor scheduler. And I'll talk as we go through a little bit about how the HTCondor scheduler is oriented toward high throughput computing and therefore can handle and encourage and has lots of built-in support for executing large numbers of self-contained tasks as we defined for high throughput computing yesterday. So we'll talk about how the HTCondor job scheduler works, even a little bit kind of behind the scenes or under the hood on a large computing system. How you run, monitor, and review jobs, some tips and best practices for submitting multiple jobs. So there are tools built into Condor, and then we've also got some good practices just around data organization that integrate with the tools in HTCondor job submission. And along the way, we'll talk here and there and then explicitly at the end about things like testing, tuning, and troubleshooting before scaling up. So first, some history. The Condor scheduling software, and really it's part of a Condor software suite these days, started in the 80s as a cycle scavenger, and it was named Condor, as we learned yesterday, partially because it was scavenging computing cycles. And in the 80s, that looked a lot more like creating virtual clusters out of disparate sets of desktops. Maybe they were on the same local network, but sort of combining those into what could effectively be thought of as a virtual cluster. And it's carried forth today, now where it's executed in many places all over the world on some very large computing systems. Its research and development has continued on in the Center for High Throughput Computing at UW-Madison, where high throughput computing as a terminology and sort of computer science theory and approach really originated. We have professional developers at CHTC now that develop Condor and the other suite of softwares that work with it, including software that drives the open science grid that is generally Condor based. So it's used all over the world, not just by the entities we discussed yesterday that participate in the OSG, but also by entities that have their own computing capacity that's not necessarily shared, like some science gateways, Einstein at Home, Folding at Home. Some of that has run on the open science grid in the past. There are a large number of companies that use Condor. For example, every DreamWorks movie is rendered on a Condor computing system, which last we knew still continues to backfill even the desktops of employees at DreamWorks who work with rendering and animating for those movies. But companies like Boeing and SpaceX use Condor, have come to the annual Condor Week conferences, the FBI, a number of other government entities, the USGS. And then there are even some entities that use Condor that I don't know about because they have non-disclosure agreements with Condor. But it's definitely, like I mentioned, used across the open science grid. And the sort of fearless leader of the Condor project is also CHTC's director to this day and the OSG technical director, Marone Livni. So if you get any more involved with the Condor community, perhaps going to Condor Week, you'll definitely run into Marone. So let's talk about how Condor works. Like other compute schedulers, for those of you who've interacted with them, it provides a queue for the user to submit tasks to on what we call an access point. This is analogous to like the submit server. On some other clusters, you could think of this as the head node, but Condor separates some of the tasks involved in scheduling in a way that adds a little more redundancy than some other schedulers. And then Condor matches tasks and schedules them to run on computers, which we refer to as execute points. These might be different computers with different amounts of computing resources like CPU, memory, file space. So it kind of does some matchmaking. And then aspects of Condor running on each of these components make sure that your jobs run and have built-in redundancies and those sorts of things. So let's talk about that from the perspective of some new terminology, and then we'll go into a little more detail about how matchmaking works. The tasks that we're referring to in Condor are referred to as jobs. These are independently scheduled or schedulable units of computing work. When I was mentioning yesterday that we think high throughput computing is as executing work in the form of highly numerous self-contained tasks, we mean self-contained in that each one has an executable to run. And if you had a large set, it could be the same executable that just takes different input or arguments. So each task needs to have its own input and or arguments that tell that software what's different about how it runs for that job versus others. And then each needs to produce output in the form of files that can be handled by Condor. So in order to run many jobs, like on most large-scale computing systems, the executable must also run on the command line without any graphical input. There are certainly examples of people, even in their own research computing organizations, creating tools or GUIs that behind the scenes are still Condor running things in the command line. But like most large-scale computing, running on the command line is what really allows the user in the end to have sort of large-scale automation, given that they're not individually starting up tasks, certainly not from a point-and-click graphical interface. Some more terminology. So we talked about jobs. On the other side, Condor thinks about machines, which are whole computers like a desktop or a server that each typically have multiple processors, some amount of memory and file space. And then Condor divides those up into slots, or basically an assignable unit of a machine. Generally, one job matches to one slot, and a slot may consist of one or more cores with some amount of memory or disk that can be a portion of what is represented on the entire machine. So each machine will have multiple slots. And the administrator can define that slots are dynamic, such that Condor can break up and create new slots as resources become available from completed jobs and also in response to what new jobs need to run. Or they can be defined statically, meaning the administrator could say this server is divided up into exactly 4 slots of the same size or some other variation that then Condor doesn't have to think about dynamically rearranging. But it's really popular in most implementations of Condor on a computing system, like in our local CHTC system and OSG, that we enable this dynamic feature. It means that we get better resource utilization. We can match more jobs to more resources. So going in a bit more detail, there's actually a component in Condor that does the matchmaking and is sort of like the brain, but it also gets out of the way when it doesn't need to be involved. So there may be one or more access points in a Condor pool, but there's generally one central manager that defines that pool. And to the user, when they think about the capacity in that pool, that's represented in the set of execute points. So access points are constantly reporting the jobs that they have to run. And again, there can be multiple access points, multiple independent queues that can submit to that pool. And then the execute points advertise to the central manager what resources they have available and other features so that the central manager can match jobs to machines. And in some cases, jobs may say they only want certain types of machines, or machines may say that they prefer certain types of jobs or jobs from certain users. There are a number of features here. But in the OSG, we try as much as possible to help people minimize how many special requirements they have so that they can match to more resources. But basically, matches are made on a periodic basis. In some larger pools with lots of jobs in queue and lots of execute points, it might take several minutes between match cycles. And then after that, the central manager gets out of the way. It tells which, the access points and execute points, which of them are supposed to match up to run jobs. And then everything about the job execution happens just between the access point and the execute point. So if the execute point goes away, crashes, the queue on the access point and tasks associated with Condor recognize that and just report that job as idle back to the central manager so it can run again, which is different than how things would be handled if the executable in your job itself failed, right? If there's some reason why your job couldn't complete that has to do with stability of execute points, the access point doesn't even have to know what that reason is. It just knows that your executable didn't exit on its own, and so your job gets requeued automatically. And then similarly, after jobs finish, or if the access point goes away, the execute points know that they've got resources that they can report again as being available to the central manager to get a new match. And by the way, all of this can fit on a single computer. So if you've got a lab server or a powerful desktop and you're hoping to manage highly numerous tasks a little bit better, you can take everything you've learned about running jobs through Condor and put that on a single computer where you can define slots and have both the queue and the central manager set up there too. So it really does, Condor really can run the gamut of different computing system sizes. And it to this day can backfill desktops as well, so that those look like a big virtual cluster. So let's talk about the basics of job submission from the user perspective. We mentioned before that jobs in Condor need 3 components in order to be self-contained. So we've got maybe an example here of a program called compare states that takes in 2 input files. Those would be the first 2 arguments in this hypothetical situation if you were to run this software on the command line, and that it knows what file to write output to by you telling it what file name to use for output as well. So we'll use this example to show you sort of the basics of the submit file and then what job submission looks like too. And there are 4 major components to a Condor submit file, especially if you're in a Condor system that doesn't have a shared file system. And I'll talk about that in a little bit more detail later. Condor can work with a shared file system, or as an OSG and in the local CHTC system, Condor can transfer files for you between the access point and the execute points. But first, some of the basics. We list the executable and its arguments, just like we would run this on the command line, but sort of separating those 2 components. And you'll see a little bit later that there's an advantage here that then you could have variations in what the arguments are, but for the same executable. And additionally, Condor knows automatically if files need to be transferred that it should transfer the executable. So in that case, the executable always gets transferred. Additionally, we need to identify any other files that are necessary for this job to run, whether they be additional software dependencies or actual data that the software will use, whatever's in our executable. And that executable could be a bash script that unpacks software. You'll learn about some of these approaches on Thursday. And then a special note, we don't have to list the output that we want back. By default, Condor will bring back any new or modified files in the top level of the working directory of the job, which I'll show you in just a second. So in this case, our wisconsin.dat.out file would come back automatically, assuming that it gets created in the same directory where our compare states program runs. But otherwise, you can, in the submit file, tell Condor to transfer back only certain files. And then there are 3 sort of meta information files that are relevant to running a job. The log file is Condor's log of what steps it takes to run your job. And it also provides a summary at the end about how many resources that job ran. You can tell by looking at that log file how long each job ran, and I'll show you one of those in a bit. But we also need to be able to capture the output or error information that when running this command on the command line ourselves, we would typically see to the terminal. So that's called the standard output or standard error. And we can define what we want those file names to be called when Condor creates those for us and transfers that information back at the end of the job, in addition to any other output files that are made, like our wisconsin.dat.out file. And then we need to tell Condor what resources we need. In most pools, and certainly in the pools relevant to what anyone would use for the OSG school, it's important to request CPUs, disk, and memory. Again, because each one of your jobs will be using a portion of a machine, ideally to get the most throughput, Condor needs to know what portion you're going to need. And conveniently, because the log file will tell you how much your job's used, it makes it really easy to tune these things and test them before you would submit lots of jobs. Oh, and then the final thing is that you need a queue statement. So any of the lines above this can be in any order you want, but the last line needs to be a queue statement to say queue 1 job, and you can queue without the number 1, and that will give you 1 job. We'll see later what queue statements you could add to queue multiple jobs. All right, so what does this look like when we submit and monitor jobs? And then I'll show you also what file transfer looks like in this context. All of the Condor commands that you would run as a user are in the form of Condor_something, where the something is semantically relevant to the task that you'd like to complete. So to submit a job, it would be Condor_submit, and then the name of the submit file. So here's what that would look like on the command line. We'd see a message that 1 job was submitted to a cluster, and we'll talk about that in a second. That is not the computing cluster, but actually refers to this set of jobs submitted to the queue. And then we can run condor_q to see Condor's sort of summary of our own jobs in the queue. On most Condor systems these days, running condor_q by itself will show you just your jobs, so you don't have to see long lists of other people's jobs in the queue. And we get here a summary such that if we had submitted multiple jobs with a submit file, there'd still be just one line that tells us how many of them are done, running, or idle, which is what we would see immediately after submitting this job. So there's one total job. A little more detail here. So I mentioned that the jobs get batched together. We will also get to see the job IDs, or a range of job ID numbers. And every job is defined by two values. One is the cluster ID. That's the same as that cluster number we heard back when we typed condor submit. And that means that this is the umpteenth or 128th set of jobs submitted to this queue amongst all users submitting to that queue. So this queue is pretty young. If it has only had 128 clusters, you might see numbers that are much, much higher for the clusters that you might submit to the CHTC or Open Science pools. And then that last number is the process ID. If you submit multiple jobs with the same submit file, they'll each have a different process ID, but the same cluster ID. And that process ID starts at 0 and increments upward with integers. And we'll show a little bit later how that can be actually really useful for submitting multiple jobs. You can also limit condor_q commands by username. So that already happens by default. But you could pick somebody else's username and look at their jobs if you wanted to. There's an option -all that would let you see everybody's jobs, but you could otherwise restrict to just certain clusters if you had multiple clusters queued, or very specific job ID. So that cluster.process number job ID. And in some later slides, you'll see these options for constraining represented by UCJ here. One of my favorite ways or sort of options in condor_q is this no batch option. And what that does if you submit multiple jobs is expand things out so that you see a different job ID on each line and you get to see more details per job instead of having just those total done, run, idle counts. So we could see here that here's the user that submitted this job, at what time, here's how much time that job has spent running, what state it's in right now, idle, meaning it's still waiting to run. You can set different job priorities to tell Condor which ones to try to run before others. The size will be the amount of memory that's used in megabytes, which is the default unit for memory, the way Condor stores it. So you could see that your job's actually doing some stuff just by running condor_q. And then the command here that's truncated in this view, given the width of our window, would show us the actual command that's being run for each of these jobs. So we'll use the no batch option to see what's going on logistically for this job as it runs. So the job starts out idle, and let's say that we had the components of our job organized this way on the access point in a directory where we submitted from. So we would have a submit file, we would type condor submit from within this directory, and by default, Condor would expect to find the executable in that same location, or at least relative to it, as well as the other files that need to be transferred. And after submitting, it would go ahead and create the log file and some placeholders for our out and error files. The log file will update dynamically, and the output and error files are where our standard output and standard error will be transferred back to at the end of the job. If you're lucky, when you run condor_q, you might catch your job in this less than state, which means that it's transferring files to the execute point. Condor creates, in the absence of a shared file system, an execute directory just for your job that's kind of like your job's playground, and it will transfer over the files you told it to in addition to the executable. Then it will run your executable, which should generally expect to write the output that it cares about in that same directory. You won't know what that execute directory is ahead of time. So again, it's sort of like your playground, and your executable should expect to handle things relative to the current working directory. Standard error and standard output will be stored in file names that may differ from the file names that you tell Condor to use in the end, but that's where that information is captured. And you might additionally have folders of output as part of what your job creates. An important point, though, is that when your job reaches the state of transferring data back, it's going to transfer back in default just the standard error and standard out that we asked for, and any new files that appear or modified at the top level of the execute directory. So it will by default ignore subdirectories, which is kind of useful because that means that you can send data that you don't need into a subdirectory. If you do need a directory of output back, the best options are to have your executable create a tar file where you get some compression perhaps of that directory to transfer it back to the access point, so that it appears as a file and not a directory. Or you can explicitly, like I said, tell Condor which files and or directories to transfer back if you only need certain of them back or want to make sure that you get directories back. But a best practice is to compress large amounts or numbers of files anyway. So compressing directories into a tar file tends to work out really well as a best practice. And then once the job is completed, you've got the constantly updated log file, output error, and then our output file back in the submit directory. And I'll show you later that there are different ways to sort of organize things on the access point, but this was sort of our most basic job to illustrate the logistical steps that jobs go through. And you'll notice that after our job is completed, it's no longer visible in the queue. It has left the queue. You can view information about jobs that have completed with Condor history. There's a slide on that at the end of this presentation. I won't go into detail on that for the sake of time, but during the demo, that's something that if we've got time, I can also show. So Condor queue to view jobs currently queued, Condor history to view jobs that have left the queue, either because they finished or you removed them or something like that. So if we were to look at the log file from a job, this, like I said, is the record of the actions that Condor took to run our job. And there will be more events listed than what is captured just in this example. Like there would be lines for file transfer to and from each job. But for example, you'd see when a job was submitted, when it started executing, and the difference between that and when it terminated would be the amount of time that it spent running. There will be information here about CPU usage for those who really care about CPU usage. But otherwise, the resources that are harder to predict, right? Because with CPUs, you tend to know if your software is using multiple CPUs and explicitly how many. But with memory and disk, you can see how much your job used versus what you requested. And in some cases, you may have been allocated even more just because that server has so much memory or disk to give. But in this case, I could have really requested a lot less disk and memory for this particular task. And if I wanted to submit large numbers of them in the future, I'd probably be best off reducing my request values. And similarly, if I changed my code or the size of my input, I would want to retest and initially request higher volumes. So a little more on resource requests. Again, this is important in a high throughput system, a little bit more so than if you're running whole node jobs in a typical HPC cluster, because you are using just a portion of each machine when you run on a slot, or at least in most cases you will be. And so your job gets to use just part of it and needs to not bother or interfere with jobs that also need memory and disk. So Condor is matching based upon how much memory and disk that server still has, even with other jobs running on it. If you request too little and your job goes over, then Condor will put your job on hold. We'll talk a little bit more later about when and why Condor puts jobs on hold, but using too many resources is one of the reasons that it does so. If you request too much, your jobs will run, but you could have matched to more slots and maybe to slots that other people's jobs couldn't, which is sort of how you, in a positive way, kind of game the system in a high throughput computing system or pool. So testing is really important. Anytime you're going from running something at a small scale or small numbers to large numbers, that really makes sense, whether you're doing experiments in a lab or whatever, but in computing, it can pay off really significantly, and especially in high throughput computing. So test, test, test. And this is important too, just throwing back to what we talked about yesterday, when thinking about whether your jobs are OSG-able, whether you might need to break them up more or combine them more, or consider maybe using multi-threading that already exists in your code if your jobs would be a little long for the open science pool, but you want to make that useful to yourself. So don't forget about the sort of specific range of job shapes and sizes that are best suited to the open science pool. All right, I'm going to take just a pause here before we jump into submitting multiple jobs in case there are any questions that have come up. I don't see anything in the chat yet, but if you've got a question that you'd like to ask verbally, raise your hand and we'll call on you. Tim can do the magic of letting people unmute themselves, or you're welcome to put a question in the chat and then I can read it and answer it. Not seeing any so far. And if you're returning today, yesterday, there were lots of good questions. The group was pretty well engaged. And it's okay, we can go on, and then there will be plenty of time for other questions later too. So maybe people are just really anxious about hearing how to submit multiple jobs. Let's jump into that. All right, so we learned how to submit one job and what the logistics are for the steps that a job goes through. Let's go back to a pretty simple submit file, but imagine that now we've got a program that needs to analyze 3 different files. We want to run that as 3 different jobs to get a high throughput component. And really, we're just showing 3 here, but the same sort of logic would work if we had 1,000 or 10,000 jobs, and therefore 1,000 or 10,000 input files. Let's say that normally we might run this job, if running it once, as the executable, we'd pass arguments telling it the name of the input file and what it should name the output file. But in this case, we'd have to choose each of one of these to get our job running. So how do we create 3 jobs that each analyze a different input file? Well, one approach certainly is that you could create multiple submit files, but this is really not recommended because one, if you need to run multiple jobs that are more than 3, it can get tedious to create submit files, and not everybody has the scripting capabilities or interest to script the production of these files. And so Condor has really neat built-in features to help you submit jobs, whether they're numbered or not. So first we'll talk about the numbered case. And as some of you might have guessed, that process number that we talked about earlier can be really useful in communicating to Condor what about each of your jobs is different, especially if what's different about your jobs is already integer numbered or is easily integer numbered by you. Like if your input files can all be integer numbered. So again, if you queue in jobs, they'll all have the same cluster ID, but different process IDs. And you can reference these numbers in the submit file using variables of the form $, cluster or process. And technically you can use cluster ID or proc ID, but cluster and process are more human readable words and tend to show up more in the documentation. So let's see how that might work. Taking that same submit file that we saw before, we've got the same executable, but now we can run it 3 different times where there's a different process value inserted as part of the input file name and the output file name. And we'll use that wherever those file names show up, including in our transfer input files line. In this case, there can be 1 log for all 3 jobs. And in exercises that we have available for the school and the demo that I'll show you later, the information about multiple jobs queued in the same cluster can be sent to the same log file if you want. But in this case, by putting the cluster number in, I could submit the same set of jobs and have a different log file each time if I wanted to. So you could choose to do that with the other file names as well, use cluster. But in this case, I'm just showing how to use it with the log. And then we can also use it to make sure that we have unique files to capture the standard output and standard error for each of our 3 jobs in this scenario. So that's sort of the basics of how to submit multiple jobs at once. Let's talk now about how you might organize files within different subdirectories now that you're thinking about how to submit what could be a much larger than number of 3 jobs. And most people want to create subdirectories and organize data in certain ways. And so I'll show you a couple of examples that we see frequently are preferences by users and how they organize things. So first, as an example, you could have different subdirectories for different types of files across all of your jobs. For example, we could have different directories for standard error and standard output files, log files, input. Maybe here's an output file that gets created by our jobs anyway, like we saw before with our file 0, 1, and 2 example. And here's how we can communicate that to the submit file. Let's say our submit file is here in our submission directory. By default, I already mentioned that the executable will be found relative to where you type condor submit. And so we can list it just like this. Our arguments will stay the same. And I'll show you that regardless of how we've organized things on the access point, they'll end up together in the top level of the execute directory, just like they did before, which is why our arguments can stay exactly the same. But we can tell Condor now to find the input within this input directory instead of being at the same level as all of our other files. Similarly, we could tell Condor to create the log files and send the standard error and standard output into their own subdirectories as well. But output by default will come back to the top level. And if you like that, great. If you don't, there are also options for sending that output to different locations too. So just drawing back on the fact that our arguments got to be the same, that's because what Condor is giving you in this case is the ability to organize things on the access point however you like in different subdirectories that are easy for you to navigate and manage all of your data. But where any of the files that get transferred, so the executable and any additional files, still get transferred into the top level of the execute directory, which means that your executable doesn't need to and really can't have access to or know about the way that things are organized back here, but it just has, again, this really simple single directory that it can work within to find both input and write output to. So regardless of how things are organized on the access point, files always get transferred into the top level of the execute directory. Another option for organizing job files that we see people preferring a lot is to have the files for each job organized into their own subdirectory. So we might have one for job 0, 1, and 2. And drawing on that same example with our analyze executable, in this case, we can define a new variable called InitialDir. We can also then leverage our $process variable to say that Condor should look for 3 different instances of initial directories numbered according to the process value. And within that, it will still find input files. In this case, they can all be named the same too. So an advantage here also is that your executable doesn't have to be able to deal with different file names. It can always deal with the same input file name and always write the same output file name, but then your results are still organized and don't overwrite each other back on the access point. And of special note, the executable is still always expected to be found relative to the submission directory, which is great because that means that Condor is not expecting that you have an executable file in every one of these directories. You can still just have one copy of that executable in the location of the submission directory or relative to it. And so the thing that you've probably been wondering is, well, what about situations where my jobs vary by something that's not just an integer starting with 0? And again, you could write lots of different submit files, but that's not cool or scalable. And Condor has really neat tools that allow you to sort of expand the queue statement and define your own variables that you could use in place of process or cluster, for example. And the exercises for these are really going to best illustrate what this looks like in a submit file. But for example, you could queue a variable that you name, like state, if we were analyzing data from different states, queue state from all files in your submission directory that match a certain pattern using a traditional shell wildcard. So in this case, we're saying for every file that ends in .dat in my submission directory, queue a job and insert the name of that file everywhere in my submit file that I say $state. And so you could use that to define the file name, pass it as arguments, just like we saw when using the process variable. Similarly, you could say for every directory that starts with job, whether it's numbered or not, queue a job, and then anywhere that I use $directory in the submit file, use the name of that directory and insert it in my submit file instructions. Additionally, you could define all of your variable values in the submit file. So you could say queue the state variable in this list. And so there would be a different job submitted for each item that you present in the list within the submit file. That list can get really long. It can span multiple lines in the submit file. And then the last one that is our favorite is to queue a variable from a list, which is a separate file then that has hard coded all of your options, just like queue state in here, hard coded that, but now you've got a separate file. And for example, you could create this file by running ls wildcard.dat and redirecting to that list. And so the reason that we recommend this one in particular, one, it supports multiple variables very easily. So you could queue multiple variables and then have your list file be a comma or space separated list of pairs or triples of different variable values. And I'll show you an example of that in the next slide. It's highly modular, meaning that you could reuse the same submit file, but just change that list file. And because you've got a list, while that additional list file is needed, you've got a hard-coded record of what you did. So that one tends to have the most advantages for what most people are looking for. But if you like writing scripts that write your submit files, that may be something that makes the variable in, or the Q variable in option, a little more suitable to you, even with large numbers of variable values. And then at least you've still got them hard-coded and recorded for reproducibility in the submit file itself, but the submit file is not really as reproducible or reusable. The matching is kind of the quick and dirty, easy way to get started with this. But the main downside is that it's less reproducible because you don't necessarily have a hard-coded list of what all of those file or directory matching values were so that you could figure out what you did later. And again, multiple submit files, definitely not recommended. So generally, if you can submit more jobs in a single submit file, you'll be much better off. And because you can organize data however you want on the access point and communicate that in the submit file, it really does make it possible to submit so many different jobs, even multiple, what you might think of as sub batches, as one submit file of lots of jobs with, say, different directories associated with how their data is organized. And just to show you, this is what it would look like, for example, if you used the Q from approach with two variables. So you could say Q, one variable name, and then another variable name, and again, provide the values that correspond to those variables in that separate text file with comma and or space separation, whichever is easier for you to put together. And I've seen people use Excel to create a comma or space separated file, which tends to still be a lot easier than having to script the creation of lots and lots of submit files. So this is another pause point before we talk about testing and troubleshooting. Are there any questions on this content about how to communicate the execution of multiple jobs and organize data relevant to those? There's sort of infinite possibilities in terms of how you combine these features that I discussed to organize data however you want. Here's one question in the chat. Is there a Python API that can be used to submit jobs directly? Yes, there absolutely is. And Jason Patton, who's here, is somebody who's contributed to some of those tools. But yes, you can submit jobs directly from Python. You can also directly view queue information from Python and format or organize that however you like. Another question, does Condor write the changed output top-level files to the submit directory back at the access point? Yes, by default, the output gets transferred back to the top-level submission directory, but you can tell Condor to transfer output back to other locations if you want to, just like we saw that you can communicate that it should pull input from other locations that are not at the top level of the submission directory. All right, these are all great questions. I'm going to move on to testing and troubleshooting. Again, there'll be time for more questions at the end, and I'll do a bit of a demo too. All right, so just a few things about testing and troubleshooting. There are two different ways that Condor jobs can go wrong. So jobs can go wrong internally, meaning that the executable ran and then exited on its own accord with an error. And that is very easily distinguishable in Condor versus the situation of jobs going wrong logistically from Condor's perspective, meaning that something like your job can be matched, files were not found for transfer, your job used too much memory, but something about the logistical aspects of your job running didn't work out. Condor had to stop your job running or otherwise wants you to know that there was something that you needed to fix that's not a bug in your code or an issue where your code couldn't run because a software dependency didn't work. So it's very easily distinguishable from your executable failing, meaning exiting with a non-zero code or not producing output versus a logistical issue with your job. And the places where you can easily distinguish these are in the log, standard output, and standard error files. So again, the log will tell you when jobs were submitted, started, if they were held, and what reason they were held for, which we'll talk about in a bit more detail in just a second. Where the job ran, the resources it used, which are really important for testing and scaling up, And any other interruption reasons, like if your job got evicted because it was on backfill, or disconnected, which may also mean that it got sort of interrupted because it was backfill. But then again, Condor detects that as different from your executable failing, and in that case, requeues your job and runs it again. Whereas with your executable failing, it will still remove it from the queue and consider it to be complete, even if not successful. But the log will give you the exit status from your executable, and assuming that your executable gives a non-zero when there was a failure, the log can be one of your first indications that there actually was some sort of failure of your executable. But otherwise, again, depending on the software that you're using in your executable, or if it's a shell script, the software inside of it, you're going to want to look in the standard output or other output files, and also the standard error, to see what information your executable printed that indicates errors. And this also assumes that the software you're using actually has useful error messages too. But at least this information is truly separate when running jobs with Condor. And so one of the reasons your jobs might not run to completion are if they get held by Condor. We've referred to holds a couple times now, but basically Condor will hold your job if there's a logistical issue that keeps it from honoring the full execution of your job as stated in your submit file. So again, this is for things like files were not found that you told it needed to transfer, including if your code failed to produce output that you specified that you needed transferred back. So in that case, there really was a failure of your executable, at least to produce output, regardless of what exit code it exited with. And then because Condor can't find that file to transfer it back, it says, I can't honor that request that you made of me, so I'm putting your job on hold. A job that goes on hold is interrupted and all progress lost, except if the case of like your job runs to completion and it can't find output, you'll at least get back standard error and standard output in that case. So Condor will transfer what it can. But otherwise, progress is lost. The job remains in the queue in the H state, partially because Condor wants to bring this to your attention until you remove or fix and then release it. And we'll tell you how to do that too. So for diagnosing holds, if you see that some of your jobs are in the held state or the H state in the queue, you can view the hold reasons in the log file, or by running condor q-hold, and you could constrain on cluster or job IDs to see all of those. This slightly longer command would give you just the hold reasons and nothing else from the typical condor q output. So we could say condor q just for my held jobs, auto format for me specifically the hold reason that Condor has stored about each job. And this is the same hold reason that would show up in the log files. But here's some examples. Job has gone over the memory limit of 2048 megabytes. Usually there's some component of human readable, user-friendly value here. Another one, no such file or directory for a file that was supposed to be sent to the job. This was a script, maybe that was our main executable or another input file or piece of code that was necessary. But maybe we had a typo in our submit file and how we specified that, or it actually exists in another directory and we just put the path wrong when we entered it in the submit file. Here's another one, failed to write a file. In this case, it looks like it's our standard error file that needed to come back to our home directory because our disk quota was exceeded. So there may be situations where your job is put on hold because of policies that the administrator has put in place and communicated to Condor. For example, if there are disk quotas, Condor can detect that that's why it can't write your job and will give you that information. And there are quotas on your home space, both on Learn and on the OSG Connect access points that those of you enrolled as participants have access to during the school. So common hold reasons, we already mentioned incorrect paths to files. I didn't mention yet badly formatted executable. So if you have a bash script as your executable, but it has Windows line endings, Condor won't be able to execute that script on Linux. It'll try, but only once it tries will it know that it hasn't worked on the execute point where your job has matched to. We already mentioned that if your job uses more resources than needed, it goes on hold. So again, more incentive to test at small scale before submitting lots of other jobs. If your job has maybe run longer than it's allowed to in the Condor pool you're using. For example, in CHTC, we have a 72-hour default limit for how long a job is allowed to run. We mentioned over quota, and then there are other reasons why an admin might put your job on hold, and the hold reason should show that so you know to get in touch with whoever supports your Condor pool. And there are other reasons, but these are some of the most common ones you might run into. Holding and removing jobs. So let's say you know that your job has a problem, like your executable has a bug, you've got a bunch of jobs that haven't even started yet, you know it has a bug, you want to keep them from running, you can fix that while leaving the jobs in the queue. However, if the problem requires that you need to resubmit, like it was a typo in your submit file, or you need to request more memory, you should remove the jobs, update the submit file, and submit. And then your submit file also is still a record of how you fixed that problem too. But if the problem is not in the submit file and is really just in the executable or within the contents of input files, or if you had the file path right in the submit file, but the location of the files, you didn't have the actual files staged yet on the submit point, the access point, you could hold the jobs, fix the executable and input files in place, and then release them to run. And as long as the same file paths from your original submit file apply, the jobs will run, use those new executable and input files, and should complete successfully if you've truly fixed the problem. So you can hold jobs yourself, you can release jobs to rerun, but you should only ever release jobs to rerun if they were held for a reason that you know you fixed. All right, so for those of you who are enrolled participants, it's your turn. For the rest of you, if you have access to a Condor computing system, most of the exercises during the school, especially today, will work on just about any Condor system. Some thoughts on exercises for those of you who are participants who went through the application process. Copy and paste is quick, but you will learn more by typing out commands and submit file contents themselves. So there are times when we give you, a chunk of C code, you don't necessarily need to keep up with what that C code is doing or copy and paste type out every line of that. You can copy and paste. But there is muscle memory in computational learning. For example, with typing Condor commands, your fingers will get better and better at typing things like Condor submit if you're doing that over and over rather than just copying and pasting Condor submit commands. Same thing with submit file contents. You'll get better and more comfortable with creating and editing submit files if you're not just copying and pasting. And in fact, as you move through the exercises, even for today's content, we give you less and less of that cookie cutter copy pasteable information and encourage you or sort of even require you to sort of take a previous submit file and modify it or write one fresh so that you get the practice doing that and can improve your learning. Definitely ask questions during work time, again, for enrolled participants only who have access to our Slack workspace. There's a channel specifically for the Condor unit and for other units this week. And you can ask questions there and also learn from the other questions that other participants are asking. And one last note, the exercises in this unit for this day are actually fairly important to complete before moving on. That's not true for some of the later days this week or for the content this week, but the stuff that you learned today is really going to be important and be built upon in some later exercises, even having them call back and say, grab your submit file from, exercise 1 point whatever on the Condor day, and then modify it. And if you find that you need to remove jobs before you get to exercise 1.6, that's the one that explicitly talks about removing jobs in a little more detail than I did today. All right, so again, I'll pause for questions that we can address from the chat or any that people would like to ask verbally. And otherwise, I'll get ready to set up for our demo.